come back to college, at least from next month. Yeah. Good morning, everyone. So welcome to yet another online tutorial on principles of communication system. This is Anup, a course instructor of fifth semester B section for PCS. So in today's session, what we'll do is we'll discuss some of the previous year question papers. We'll go through some of the previous year question papers and we'll see whether you are able to relate those questions with what you have already learned. And if you are coming across some interesting problems, like the sort of problems which you have not solved in our sessions before, we'll solve that as well. Right. So then after that, from next live session, we'll start with angle modulations, that is a frequency modulation. And in the coded session, we'll again start addressing some of the aspects which are related to VSB and SSB, which are not directly part of our new revised syllabus, right? And I can see whenever I'm posting a recorded session, most of you are not able to catch it up, right? So some are already lagging behind, right? So when it happens, what happens is when we have a live session, if I'm referring to some of the points which was discussed in that recorded session, you will be finding it difficult. So I request everyone to find some time and finish whatever sorry backlogs you have in terms of recorded videos or even live sessions. Some of you might have missed live sessions because of some valid reasons, right? So the recordings are already made available. So to watch that and catch up with the remaining people in class so that we can have a smooth flow of our actually subject. So we'll start with a question paper. So I think my screen is visible, right? So I'll just, right. So it's actually July 2017 question paper. So during July 2017, right, the subject principles of communication system, it was taught in fourth semester till last year. Till last year, principles of communication was taught in fourth semester. So from this year, it is taken to fifth semester, right? Also, there is some slight modification in syllabus. Even then, we'll see some questions. What kind of questions are asked? Now that we have almost done with our first module, right? I think it would be good if we can have a quick glance at the previous year question papers, right? So in that, from module 1, the first question asked was explain with the help of neat sketch and analysis how switching modulator is used to generate amplitude modulation. So this thing, I think we have discussed about switching modulator. A switching modulator, it is a simplest means of generating a standard AM wave, right? And it had, if I tell, you may remember, it had only a diode and a resistor, right? And it should be followed by a filter, a band pass filter, of course, right? So how it works, so that details, I think it's you can easily recall it and write it. And we have even seen some simulation, so that question won't be a problem. So if anyone has any doubt related to the switching modulator, if yes, please feel free to ask. You have to unmute yourself and ask, right? So if you type it in, I may not be able to see now. So I think I don't have to discuss much. It's already discussed, right? And you are somewhat clear with that, right? So the next question was explain how Costa's receiver can be used for demodulating DSBSC signal. So this again we have discussed, right? Costa's receiver in detail we have discussed. So we have seen Costa's receiver. It is a practical coherent detector, right? I'm just giving you some hints so that you can actually recall, right? So can anyone tell me what were the components in a Costa's receiver? How a Costa's receiver worked? How Costa's receiver was able to maintain phase synchronism, right? So it's a coherent detector, which means we have to use a local oscillator to produce a carrier frequency sinusoid at the receiver end, right? But if we don't have precise phase and frequency synchronization, there will be some problem. But Costa's receiver had some setup to maintain precise phase and frequency synchronization, right? Anybody remember that? If we can just recollect that and tell, that would be really great. right? Maybe I'll ask, right? I may ask some of you. So what about, let's see. Okay, I'll ask Sanjay Shankar, right? I'll ask Sanjay Shankar, right? Remember what is Costa's receiver,
Yes, sir.
Sanjay? Yeah,
Hello, sir.
do you remember what is Costa's receiver?
No, sir.
No. Did you watch that video? You were present while we were discussing that,
I watched, sir.
but I don't
Yes,
remember
sir. I was
now.
present, but I don't
Don't
remember,
remember,
sir.
forgot now, right? So, what can be done? So maybe what I should do is this
Yes,
would be the right time for us to what keep one assessment. If I keep one test on first module, right? Maybe right. So soon we'll announce the date. We have to keep a test. Then only you will be actually what you have a habit of what learning everything whenever a test comes, right? So maybe we'll keep a test soon so that everyone will just go back and study whatever has been taught so far. And I have one more request. So I told, anyhow, you people are attending classes online, right? Some are attending because they really want to gain some knowledge or they want to learn something in class. Others are attending for attendance sake, whatever it is, right? So you are spending this much time in classes, so please try to what be attentive and try to learn something. So that is the best way to manage your time. Otherwise, right, if you keep everything pending, right, together you won't be able to learn everything. So if it is, if you have internal exam, maybe a day you will have two exams, so you may not be able to what handle that. It's not like your pre-university or school days where you can study everything a day before. It will be difficult, right? Even if you are able to what cover everything, cover looking at everything, you may not be able to what successfully reproduce it. So please prepare. So now if we keep a test, will you be able to what um, learn and uh, deliver these things? I'm asking to the entire class. That option 3, will you be able to learn it right now? Okay, it's obvious you have other subjects also, you may forget, right? But will you, do you think as you have seen those topics once, do you think you will be able to learn it? So please, a yes or no. Or otherwise, what I should do is maybe I should conduct a sort of surprise quiz, and those who are right, maybe I should keep some cutoff. Those who are like scoring less than that, I may have to keep some additional sessions, right? So I'm ready to do that also. If you're finding it really difficult, so please do let me know. Will you be able to like at least right? Some if I get some 3-4 responses, I'll go ahead. Please, no surprises are entirely right. Right. So no, it's for me. It's not a surprise. I can right. Okay. Yeah. Fine. So anyhow, we'll keep a test. So by that time, I think all will be comfortable. So if you have any doubt, please feel free to ask. Right. The same thing can be. It can be explained in different ways. Once I had kept a doubt clearing session, if I remember it correct, only 6 students attended, right? So they have asked some doubt, we discussed, and some doubts were cleared, right? So okay, fine. So I'm not so whichever is discussed, I'll tell it is discussed. You should be able to what learn it on your own, right? So this Costas receiver is discussed, and if you see this, right, if you see this particular problem, the next problem, right? This problem was what we have solved in last class, and I've posted the sold out example. And the second part of the problem, I told it will be an assignment, right? So that assignment link will be created. Maybe today evening I'll create the assignment link. I'll ask you to what submit it. It's just a problem, right? So we have solved it, right? As I had to leave some 5 minutes early on that day, we couldn't finish that, but I've posted the sold out example. right? So you should be able to solve it. So the same problem what we have seen in last class, right? So then, so that problem was asked for just, yeah, 4 marks, right? It was asked for 4 marks. Then next question is explain the operation of an envelope detector with need diagrams and waveforms. So envelope detector again, you know, it has a diode followed by a low pass filter, right? So then what should be the RC values, right? So we have this, I have explained, right? Charging will happen through diode and the capacitor. Discharging will happen through the capacitor and resistance. So what should be the RC values? All those things again we have discussed. So, but you can see an interesting problem here, right? Second problem. All of you please take down this problem. All of you please take down this problem, right? To derive an expression. Oh, sorry, not this. This again we have derived, right? So in last class, in last Friday session, we derived it. Expression for SSB modulated wave for upper, for lower sideband retained, upper sideband retained, we derived, right? So then this again we have done expression for SSB modulated waveform for which upper sideband is retained. So there actually we had to make use of the concept of Hilbert transform, right? So we have seen it was m of t cos 2 pi fct plus or minus m cap of t sin 2 pi fct, right? So I told if it is only upper sideband retained, it will be plus, and if it is lower sideband retained, it will be minus. Sorry, if it is only lower sideband retained, it will be plus, and if it is only upper sideband retained, it will be minus. So this again we have discussed, and please watch the previous videos for that. But this is an interesting problem, right? This is an interesting problem, and maybe we'll have to solve this, right? Why? Because we have not discussed, even though we have discussed some of the problems, we have solved some types of problems. This type of problem we have not solved. Why? Because there is some twist in this problem, right? So I want everyone to please take it down, right? The question is, using the message signal m of t is equal to 1 by 1 plus t square, determine and sketch the modulated wave for amplitude modulation with the following values: mu equal to 50% and mu equal to 100%. Right. So this is the question, right? So using the message signal m of t is equal to 1 by 1 plus t square. So maybe you can give it a try, right? So you can give it a try. This is the question. Using the message signal m of t equal to 1 by 1 plus t square, determine and sketch the modulated wave for amplitude modulation with the following values: mu equal to 50% and mu equal to 100%. So this is a question from, did anyone understand from which topic this question has come? So this is a question from, I'll give you a hint. It is a question from standard AM, right? It's a question from standard AM, right? So what is the time domain expression of standard AM? I'll give you a hint. So what is the time domain expression of standard AM? If I write S of t, it will be equal to AC into 1 plus Ka m of t cos 2 pi fct, where this AC cos 2 pi fct is carrier, right? AC cos 2 pi fct is carrier, and m of t is message, right? It is C of t. M of t is message, right? And what was Ka? Ka was amplitude sensitivity, right? Amplitude sensitivity. So when we study PM and FM in next classes, we'll study similar terms: phase sensitivity and frequency sensitivity. This Km is amplitude sensitivity. Now let us see what are given. We'll just list down what are given in this question. One thing which is given as m of t is equal to 1 by 1 plus t square, right? So we can assume C of t to be AC cos 2 pi fct. We can assume, right? We can assume C of t is equal to AC cos 2 pi fct, right? So that AC we have, cos 2 pi fct we do have, m of t is there. But what is this K here? Whether this K is given? K is not given as such. What is given as mu? In case 1, mu, or it is modulation factor or modulation index, it is equal to 50% or equal to 0.5, right? And in case 2, mu is equal to 100% or equal to 1, right? So now this expression is what we have to get. Am I audible now? It's raining very heavily here, right?
Yes,
It's
sir.
right. No, even voice is not breaking, right?
No, sir.
Okay,
No,
okay,
sir.
okay. I can't hear what I am talking. Why? Because it's very heavy rain here. Right. Okay, no problem. As long as you can hear, right, not a problem. So now, how to find Ka? So is Ka and mu are same? So now I need some ideas. Right. What is Ka actually? Or how mu was defined? Right. So we have defined mu is equal to maximum of Ka times mode of m of t. So we have, I hope you remember this. This is how we have defined mu, right? This mu is given, right? But what we need is we need to find what is this Ka. So from this, can you find Ka? Maybe you all can give a try, right? How to find Ka, right? Just imagine I have not discussed this question, right? But for exam, such a question came, what you would have done? I would like to know, right? So now, just now, who asked? Samarth asked me, no, please, no surprises, right? So, but what happens is at times, life itself will give you some surprises. That surprise may happen in right your university exam paper. So, what you would have done? Maybe you can. One thing what you can do is you can scold me. That stupid fellow, he didn't teach us this. Because of that, I am not able to answer. Right, that is one option, but that won't fetch you any mark. Right, anyhow. Right. Other than that, how if you have to make a try, right? How you will make a try? So it is mu was given. Mu was given. Right now we know what is m of t. Right, we know what is m of t. K is what we have to find out. Right. Once we find out K, it's straightforward. I can just actually put the value of K here and straight away I can write the expression. But now how to find K? Right. To find K, you should find what is mode of m of t. So that's why I told there is a twist. So here m of t is 1 by 1 plus t square. So what is magnitude of m of t or maximum of m of t? What is maximum
One.
value of huh?
One.
Yeah, exactly. How is it one? How we'll find out that? How to find out that? Maybe you might have studied something about maxima and minima. So now you told maximum of m of t is 1, right? So okay, if m of t was, like, I'm just modifying the question now. If m of t was t by 1 plus t square. So this also was asked once, even long back. When it was analog communication, this question was used to be asked, right? If m of t is t by 1 plus t square, right, then what will be max of m of t? So now in this case, when if m of t is 1 by 1 plus t square, right? So it was told the maximum is equal to 1. That is correct, right? But what will be maximum value of mode of t by 1 plus t square, right? What is this? How you will find? So if you know this, then the problem is going to be actually what? Quite straightforward, and it will be easy, right? How to do this? How to find this? Right. So there is a mathematical actually what method. So if we assume m of t is equal to 1 by 1 plus t square by plus t square, right? So the maximum of m of t will occur. So max of m of t, of course, the minimum also, right, will occur at right some value right at right this t for which I'll write here, for which d by dt of m of t is equal to 0, right? This maximum of m of t will occur at some value of t, at some t, right? For which d by dt of m of t is equal to 0, right? So maybe I can imagine some of you at least will have some issue with this. So maybe we can just see what this 1 by 1 plus t square or t by 1 plus t square it looks like, right? So can anyone tell me how this 1 by 1 plus, how can I plot this 1 by 1 plus t square? If this is t, right, with respect to t, how 1 by 1 plus t square changes? First, if we substitute t equal to 0, right, so this m of t will be, so this is m of t, this is m of t, right, and this x-axis is t, right, this is 0, right. So now when t equal to 0, what will be m of t? It will be 1 by 1 plus 0, that will be 1, right. And as t increases in positive or negative direction, what will happen? This denominator will increase, right? So you can see as t increases or as mode of t increases, either in positive or negative, right? Denominator will increase. So mode of m of t will decrease, right? So the graph will be something like this. Right, just now someone told the maximum value of this 1 by 1 plus t square is 1, right? It is absolutely true, right? So the maximum value of 1 by 1 plus t, it happens at t equal to 0, and that is equal to 1, right? So if it is instead of 1 by 1 plus t square, if it was t by 1 plus t square, right, maybe you may not be able to plot this and find out the maximum value. Right. For that, we have a mathematical tool that is actually what the knowledge of maxima and minima. Right. So how to do that? So this maxima or minima will occur at some value of t for which d by dt, first derivative of m of t is 0. Right. So we'll find out what is d by dt of 1 by 1 plus t square. What is d by dt of 1 by 1 plus t square? Right. So you can take it as, you can either actually what, solve it by means of substitution method, or else you can take it as d by dt of u by v. So now I'll take it as d by dt of u by v, u by v. So what is d by dt of u by v? D by dt of u by v, it will be, what is d by dt of u by v? If anyone can help me out, please. It is denominator into derivative of numerator minus numerator into derivative of denominator divided by denominator square. I hope this is the what rule, right? A derivative of a fraction of functions, right? So if you apply this, right, so first it will be 1 plus t square into derivative of numerator will be what? D by dt of 1 will be 1 minus first function is 1, d by dt of 1 plus t square whole divided by 1 plus t square the whole square. So what is d by dt of a constant? So this is equal to actually what? 0, right? So it will be 0 minus what is d by dt of 1 plus t square? It is 2t, right? 0 minus 2t divided by 1 plus t square the whole square, right? So what we need to find is for which value of t, this is equal to 0, right? We need to find the value of t for which this is equal to 0, right? So if this should be equal to 0, right, one option is either this denominator should be equal to what? Infinity, or numerator should be equal to what? 0, right? So the denominator being infinity, right? At denominator being infinity, what we will get? This 1 plus infinity square, so it will be infinity. So it will be right. So at that point we'll get maxima. So we don't want to consider this. But when t is equal to 0, when t is equal to 0, right, this entire thing will be 0. So either numerator has to be 0 or denominator has to be infinity. So we won't consider the case where denominator has to be infinity, right? So we will consider the case where numerator is equal to 0. So for t equal to 0, right? So which implies t equal to 0. So now if you substitute, right, t equal to 0 in this expression, 1 by 1 plus t square, right? So we have to evaluate this 1 by 1 plus t square at t equal to 0. What is that? It will be 1 by 1 plus 0 square, it is equal to 1. So mod of m of t, the maximum value of m of t, that is equal to 1. So if you have any doubt, maybe we can verify it, right? So I can just try it out using GeoGebra or something. In GeoGebra, I'm just typing 1 by 1 plus t square, 1 by 1 plus t square, right? So we are getting same graph. If you see here, we are getting same graph as we mentioned, right? So at t equal to 0, it has maximum, right? And at that time, you can see when I say d by dt equal to 0 means whenever it is maxima or minima, at that time slope will be equal to 0, right? So the correct way to find out maxima is d by dt should be 0 and d square by dt square should be negative, right? At that time we will get maxima, right? So we are not discussing that much in detail. So you can see the maximum value of m of t. So our m of t is something like this, right? M of t is something like this. The maximum value of m of t is equal to 1. So for this, you don't have to plot the graph and find out. What we can do is you can do our math. So what we have done, how we found out that, right? How did we find out that? What we did is we uh, max of, right, maybe I'll write here max of mod of m of t, max of mod of m of t, right, it will be equal to value of m of t, right, at t when d by dt of m of t is equal to 0. That is what we have done. So we are getting mod of m of t is equal to, right, so what I'll do is I'll just go up and take the question alone down, right? So this much, let it be there. Only this part I'll copy and bring down, right? So that we can continue with the discussion. So such questions you can expect. It's not out of syllabus. It's within our syllabus only, right? So control V. Yeah. So now, once again, so we'll write, right? M of t is given. M of t is 1 by 1 plus t square, right? And C of t is, we'll assume AC cos 2 pi FCT. And what else is given? Mu is given. Mu is nothing but what? Maximum of Ka times mod of m of t, right? Maximum of Ka times mod of m of t. This is Ka should be a constant, right? So it is Ka times maximum of mod of m of t, right? So we found maximum of mod of m of t to be equal to what? Maximum of mod of m of t we found, right? Maximum of mod of m of t is equal to 1, right? So which that is equal to 1. So which implies mu is equal to Ka into 1, right? So this is equal to, now in this case, fortunately, mu and Ka are same, right? In this case, fortunately, mu and Ka are same, but we will see another case where mu and Ka will not be same, right? So in first case, right, right, mu is equal to Ka into 1, that is equal to 0.5, which implies Ka is equal to 0.5. So now we can straight away, right? So we have everything what we want, right? So in first case, S of t will be equal to AC into 1 plus Ka into m of t times cos 2 pi FCT, right? So this will be equal to AC into 1 plus Ka is nothing but what? 0.5. So half m of t times cos 2 pi fct, right? So now we have to actually sketch this, right? What we'll do is initially we'll try it in our GeoGebra, and we'll come back to our whiteboard and see how to sketch that, right? So we have m of t here, that is actually what? F of t, right? So now what is the expression is, right? So maybe I'll write AC, right? AC, say I'll assume AC to be equal to 1 now, right? I'll assume AC to be equal to 1, right? FC to be equal to, any suggestion on FC? What value should I take? FC I'll take as 10. Would that be fine? Yeah, I'll take FC as 10, right? So then our expression is, we will just go back and see what is our expression. AC into 1 plus half times m of t cos 2 pi fct. So again, Ka I'll define as half, right? So then later on anyhow we can change, right? So Ka also I'm defining it as 0.5. Ka is I'm defining as 0.5, right? Now we'll define it is equal to AC into 1 plus 0.5 Ka into m of t. Instead of m of t, we have here f of t, right? We do have here f of t. I'll write f of t, right, into cos 2 pi fc times t, right? So this is our modulated signal. So I'll just zoom it in a bit, right? So this is our modulated signal. This is a signal, right? So this is our m of t, right? M of t looks like this, right? M of t looks like this, right? And our modulated signal is just it exactly follows the envelope, right? So and how do you know what is the maximum value, what is the minimum value, and all? So you know how to find maximum value, right? Maximum value will be AC into 1 plus mu, right? Maximum value will be AC into 1 plus mu, right? So we have assumed AC is equal to 1 here. We have assumed AC is equal to 1 here. Please do listen carefully. We have assumed AC is equal to 1 here. I'll just write it here. Maybe I'll take a pen in this only and I'll write, right? So maximum value, say V max, is equal to AC into 1 plus mu, right? So what is right? What is that? AC I have taken to be equal to 1, and mu is equal to K, that is equal to 0.5. So it is actually what it should be, 1 into 1.5. So that is equal to 1.5, right? That is equal to 1.5. So you can see the maximum here is actually what? 1.5. You can see that the maximum here is 1.5, right? And similarly the negative maximum will be actually what? 1.5, right? So if so this is the modulated signal. So how to plot this, right? So how to plot this? To plot that, right, in you can say plot it like this. Initially maybe you can draw an envelope, right? Your envelope you can draw like this. So to plot in exam I'm just telling, right, your envelope you can draw like this, and your so please keep in mind there is no any space reversal or anything. It is actually what? A perfect modulation, right? So this is how you can plot it, right? This is how you can plot it. This is the modulated signal, right? So yeah, so m of t, according to strictly the envelope will be what? Following the m of t, right? So now instead of m of t is equal, so now it is for actually what? Mu is equal to 0.5. Suppose if mu was equal to 100%, right, that is equal to 1, which implies K also would have been equal to 1, right? So if mu is equal to 100%, K also would have been equal to 1. So then what would have been our S of t? So our S of t would have been AC into 1 plus m of t, AC into 1 plus m of t cos 2 pi fct, AC into 1 plus m of t cos 2 pi fct, right? So here K is equal to 1. So what I'll do is in this waveform, right, in this waveform, I'll just make this Ka to be equal to 1. Right. In this I'll make Ka to be equal to 1. So this is actually what for 100% modulation, this is the signal. So what happens is now this m of t is always positive. Right, what you have to keep in mind is m of t. This m of t is always positive. It will become 0 at t equal to infinity. Right. M of t is always positive. It will become 0 at t equal to infinity. Right. So where we had the issue with phase reversal or something, right? So at what point, right? At what point this carrier amplitude will become equal to 0, right? So if you see, right, if you see the maximum value will be equal to, in this case, the maximum Vmax will be equal to AC into 1 plus mu, that is equal to AC into 2, that is 2 AC, right? And minimum value would have been equal to AC into 1 minus mu. Minimum value would have been equal to AC into 1 minus mu, that is equal to 0. But this will happen at t equal to infinity, plus or minus infinity only, right? So maybe we'll just examine that whether it is the same, right? What is the maximum value here? You can see the maximum value here is 2, right? You can see the maximum value here is 2, and it is decreasing. And if I zoom it in further, you can see it is decreasing, and at the end, when t is equal to infinity, at that time only this minimum value of the modulated signal will happen, that is equal to 0, right? So this is how you will be able to plot this, right? So this is how you should be able to plot this. And any doubt in this, please feel free to ask, right? Any doubt in this? So yeah, any doubt, please feel free to ask. Right. Did you understand how to solve such problems? Right. Instead of a sinusoid, right, any other m of t is given, right? You may need to find out either Ka or mu. So for that, you should know what should be the maximum value of m of t. That can be found out by substituting the value of t in m of t, which will make first derivative of m of t equal to 0. So that's how what normally we'll do, right? If you have another some function which has many maximas and minimas, right? So if it has actually what maximas and positive minimas, right? So then what you should have done is you should have actually what taken the first derivative, and again second derivative, wherever you are getting second derivative equal to negative, that value of t you would have taken. But I don't think you will get such, right, complicated functions. You will get simple functions which will have a principal maxima and say minimas, right? You won't get a function, right? So for it to have many maximas, right? So maybe such functions we may not get. In case you are getting, that is how you have to deal with. Now my question, now for m of t is equal to t by 1 plus t square, right? Now for m of t is equal to t by 1 plus t square, right? Instead of 1 by 1 plus t square, if it was t by 1 plus t square, I want to know how you people will solve this. I just assume m of t is t by 1 plus t square, right? So just tell me what will be the, for mu equal to 0.5, what will be Ka, and for mu equal to 1, what will be Ka? Only this much you have to tell me, right? Maybe how this T by 1 plus, how to plot this, okay, that again I told, right? So 1 by 1 plus T square, how to plot this? We don't have GeoGebra and all. How to plot, if a function is given, how to plot that function? Maybe we'll try with this. Maybe we'll try with this T by 1 plus T square. So this is function is T by 1 plus T square. So for different values of T, so for T, right, for T equal to 0, what will be T by 1 plus T square? If we substitute 0 in this, maybe I need some help here. Maybe I would like to call out Sherwin Brian, right?
Yes, sir.
Yeah, so for T equal to 0, what will be the value of T by 1 plus T square? It will be
0, 0.
0, yeah. So T equal to say plus 1, it will be 1 by
1 by 2.
1 by 2. T equal to minus 1,
minus 1 by 2.
minus 1 by 2, right? Excellent. So you can find maybe for 2 more values I'll find. T equal to plus 2, it will be 2 by 1 plus 4, it will be 2 by 5, right? Plus 2 by
Yes,
5,
sir.
right? Plus 2 by 5. And T equal to minus 2, it will be minus 2 by 5, right? Minus 2 by 5. So you can see you are getting, this should be, right, an odd function, right? For positive values, it is actually what? All are positive, and for negative values, all are negative. So this graph, if you are trying to plot, it will look something like this. Right, the graph will be something like this of T by 1 plus T square, right? So the graph will be something like this. So now I want you to find out what is the maximum value of this, what is the maximum value of mode of this. So it will have one positive maxima will be there, one negative maxima will be there, right? So what will be the maximum value of this? Sherwin, can you just
It's 0.5.
0.5. How did you find that? Do you want to share the screen and explain, or you'll explain it orally? How did you find it is 0.5?
It's like we have to differentiate it. Then above equation which I get, I equated to it 0. Then I solve that equation.
Okay, would you please help me to differentiate it once? So I'll just write down, right? This m of t is equal to, right, t by 1 plus T square. So now maybe I'll write m dash of t. M dash of t, it is
1 plus T square
1 plus T square times
minus T times 1 plus 2T.
minus T times 1 plus 2T,
1
or
plus-
only 2T?
2T, sorry.
Only 2T, right? 2T all divided by 1 plus T square the whole square, right? So I should equate this to 0. I should equate this to 0, right? So you can see here from the graph which we have plotted, right? So it will have one positive maxima will be there, one negative maxima will be there. So those are the places where actually what you can see the slope was increasing, and it is actually what saturating slope. Then it is decreasing, right? So that's why in maximas and minimas, slope will be equal to 0, right? So for what value of this? So if you simplify this, it will be 1 plus T square minus 2T square, right? So I can equate numerator to be equal to 0, right? That is 1 plus T square minus 2T square. This is equal to 0, which implies 1 minus T square is equal to 0, right? So T square is equal to 1, T is equal to plus or minus 1, right? T is equal to plus or minus 1, right? So this is for T equal to plus or minus 1, you will get maxima and minima. So if you substitute T equal to 1 in this, what you will get? It will be at T equal to 1, you will get m of T is equal to 1 by 1 plus 1 square, that is equal to 1 by 2. And at T equal to minus 1, you will get m of T is equal to minus 1 by 2, right? So as we are interested in mode of this, right? So maximum of mode. So one is actually what the maxima, the other one is minima. So as we are interested in mode of maximum of mode of this, maximum of magnitude of this, that will be 1 by 2. So what you have told is correct. So what we have is mu is equal to Ka into mode of m of t. In fact, max of this, right? This is equal to, right, Ka into 1 by 2. Mu is equal to Ka into 1 by 2, which implies Ka will be equal to what? 2 times mu. So in this case, in the second case, Ka will be equal to 2 times mu. Just keep in mind. So whenever mu is equal to 0.5, whenever mu is equal to 0.5, which will implies Ka is equal to 2 into 0.5, that will be equal to 1. And also whenever, so I request all of you to try out this, right? I request all of you to try out this. Whenever mu is equal to 1, Ka will be equal to, in the second case, Ka will be equal to 2 into 1, that will be equal to 2, right? So, and the time domain expression, it is one and the same. It is S of t is equal to, again, AC into 1 plus Ka into m of t cos 2 pi fct, right? So yeah, that is the time domain expression. So maybe we can just try and plot this. Whenever Ka is equal to 1, right? Whenever Ka is equal to 1, right? You will get, okay, maybe we'll just see here and then, right? We'll just see in our simulator, right? So I'll just take, so when we wanted Ka is equal to 1, so this f of t, I'll change it to t by 1 plus t square, right? Here only I'll change of t is t by 1 plus t square, right? So maybe these things, right? So as we have predicted, this is the graph, right? Like this is the same thing. Like what we have done is we created a tabular column, we found out some values, right? So from that we got to know, right, it's positive for positive values of t and negative for negative values of t, and initially from 0 to 1 it will increase and then it will decrease. Those things we have seen, and accordingly we have plotted a graph, right? So then what we did is, so this is our f of t now. So now for Ka is equal to 1, right, this is what is happening. So if you increase Ka, right, if you increase Ka, you can see at some point, so when Ka is equal to 2, right, so you can see that there are some phase reversals. There is some phase reversal. One second. When K is equal to 2, exactly at actually what this, whenever this is negative maximum, you can see instead of the phases continuing, there is a phase reversal, right? That happens at the negative maximum. And similarly, when K is equal to 1, there is no phase reversal. Why? Because our condition for not having phase reversal is satisfied at that point, right? But whenever Ka is equal to 2, that is getting violated. So I'm just, right, I can just share this thing with you, right? Or else you can only try it out in GeoGebra. I request you to play around with this so that you will develop some intuition, right? How to go about such problems, right? So instead of, if normally what we have solved as the problem will have either a sinusoid with 2 frequency components or 3 frequency components, but if the message is some function which is other than sinusoid, this is how you have to deal, right? Okay, yeah. So that's what is that problem. Is it clear whether we should have discussed it or else I should have assumed you would have solved it, right? So now I need response, right? Right. I want you people to respond, right? If you are seeing such a problem for the first time in your university exam question paper, would you have solved it, right, or left it? Or else would you have taken K is equal to mu? So you would have left, right? And some people actually what they would have taken K is equal to mu. So in that case also it would have been wrong. So that's why. So while discussing, as I told, if you're coming across some problems which need some attention, so that you will get an idea, right? This kind of problems are also uh, possible, right? So, okay, fine. So now that's it. So for t by 1 plus t square, right? For m of t is equal to t by 1 plus t square, I request you to try it out on your own, right? So now we'll move on to the next question paper. So I'll take some, say, 5 more minutes. That's it, right? So this problem again is solved, right? So now maybe I'll share these question papers with you people. So we'll move on to the next question paper, right? So this is again June, July 2018 question paper, right? So in that it is asked, define amplitude modulation, explain the generation of AM wave using switching modulators. Switching modulators asked. So what is coherent detection? That again we know, right? Obtain the expression for spectrum of AM signal so that total power in the sidebands is 1/3 of the total power in the modulated wave when 100% modulation, right? So this again we have solved, right? So I'll just, if I tell you, you will remember, right? You know, carrier power is equal to what? AC square by 2, and P sideband, right? We have solved many problems, I think, in this, right? AC square mu square by 4 total, right? So when what is asked is, when mu is equal to 1, you should show out, right? P sideband by P total is equal to 1 by 3, right? This is what we have to show. I think we have solved this problem, right? So, and that video again, I made it available, right? So I request you to watch that, right? So then, what are the modified forms of amplitude modulation with need circuit diagram and waveform? Explain the operation of ring. So what are the modified forms of amplitude modulation? So we had standard AM, that is the basic one, the simplest one, right? But in order to have better power performance, we went for DSB-SC, right, where carrier is suppressed, right? And further, to have improved spectral efficiency or improved bandwidth efficiency, we went for SSB and VSB. So these are the first class itself, right? We started with the comparison. So that sort of comparison is what is expected here. And with the neat circuit diagram and waveform, explain the operation of a ring modulator, right? So what they have asked is with the neat circuit diagram and waveform, right? So even if you miss out, so but we have explained it in detail, the ring modulator, right? So then this VSB modulation and demodulation process and the square law detector, as per your revised syllabus, it is omitted. But even then, right, in next offline session, I will discuss these things, right? I will discuss these things in next offline session, and in next live session, we will straight away start with this frequency modulation, right? So this VSB, SSB we have already discussed, even though it was not explicitly mentioned in our syllabus, right? Anticipating the possible questions from possible questions in university exam, and also it is important in as when you consider competitive exams like GATE, right, and other PSUs, right? So that's why we have discussed that, and again these things also we'll discuss, but in recorded sessions, right? So, and maybe one more question paper we'll see, right? One more question. Right. So in this we have, yeah. So this problem, I think we have solved. Audio frequency signal, M of t is given, right? Carrier is given, modulation index is given. Find sideband frequencies, amplitude of each sideband. This problem, I think, during problem solving session, we have solved, right? So, and you can see switching modulator, it is asked every time, right? It was asked every time, but I am not asking you to what. So it's just, these are the possible type of questions. If you find, if you are not able to answer any type of question, please do let me know so that I can just try and solve this, especially problems, right? So it's not possible to solve each and every type of problem. The basic idea is, right, you have the basics, right, and you know the concepts, then you should be able to apply whatever basics in this new scenario. That is That is how it should basically happen, but I can't see it happening most of the time, right? I can see some complaints if, right, oh, this particular like aspect was not discussed. You can complain, not a problem, but just think, right, simply by complaining you are not going to what, gain anything. The loss is from your side. So maybe the effort which is supposed to be from supposed to be put from your side, please do, right, put. I told, maybe if you want some more sold out examples, I can share the sold out examples, right? But you should be in a position to right, at least, right, if even if it is a considerable bit of twist is there, or it's a application level question which is being asked, you should be able to what, solve this, right? So then again, DSBAC using ring modulator, right? Okay, this is one thing, right, which is omitted from your syllabus. That is called actually what, frequency translation, right? Frequency translation. This particular problem, it deals with that. So rather than solving a problem, right? If you remember when we discussed in the first session itself, right? Whatever frequency is being used for FM, that is 88 to 108 megahertz, and whatever is used for AM, we use somewhere in actually what, kilohertz, right? AM, the frequency band used was somewhere in kilohertz, but for FM it is in megahertz. Why? There is a question. Why for FM, for AM, low frequency is used, and why for FM we can use high frequency, right? So this particular concept, that is called actually what, frequency translation, or like maybe a filter design for SSB will, single sideband modulation will help us with that. So I'll take hardly 3 more minutes, and after that I'll wind up, right? With your permission, I would like to take 3 more minutes. So if you remember, right, SSB, right, SSB can be used for voice signals. Typically the voice signals will have a null around DC region, right? That is, say from 0 to 300 hertz or 0.3 kilohertz, it doesn't have any frequency contents, right? So what it has is from 300 to 3.4 kilohertz. So some may ask, so if it doesn't have DC, how can you call it a baseband, right? So even though instincts, as when you speak in terms of definition, right, even though this is not baseband, but it has considerable lower frequency, and we have seen what is the difficulty while if we are trying to transmit lower frequencies as such wirelessly, right? Starting from antenna height to maybe the power level, all those things. So we have many difficulties. So we'll be using actually what, we can use SSB modulation for this. So if I use a carrier FC, what will happen is the SSB spectrum will be something like this, right? So this entire spectrum will be shifted right by an amount FC, right? And also there will be a negative part, so it will be right. So this is how the spectrum will look like. It will be centered around FC. So if you consider, this as actually what, F minimum, and this as F maximum, right? So what will be this spectral separation? What will be the spectral separation? This will be 2 times F minimum, right? If you inspect this, you will get to know this spectral separation will be 2 times F minimum. If I call it actually what, if F minimum, so this, if I call it 2 alpha, right? If I call it 2 alpha, I'm just calling it 2 alpha. Why? Because I have to relate it with some rollover factor of filter or whatever, right? So so this, you know, this is upper side band, right? And this is lower side band. So practically, if I have to design a filter which should allow only upper side band to get a single sideband modulated signal, I should use a filter, right? That filter will have a finite roll-off. So that finite roll-off, right, you can see it can be something like this, right? So this filter, right, this is FC plus F min, right? So it should have a finite roll-off like this. So if, just imagine if this gap was very small, just imagine if this gap is very small, then it is very difficult for us to realize a practical filter, right? In ideal, so when we derive the time domain expression, so we considered a filter which is like this, right? But in practice, we can't come up with a filter with a sharp cutoff, right? There will be a finite transition, there will be a finite roll-off, right? So ideally we can't have this. So there is, as a rule of thumb, I can write 2 alpha by fc, right? 2 alpha by fc should be always greater than or equal to 0.1, right? So which in this case, which in the case of SSB, right? Which in the case of SSB, alpha is equal to f min. I told it is equal to 300 hertz or 0.3 kilohertz or 0.3 kilohertz, right? So what will be 2 alpha? 2 alpha will be 0.6 kilohertz, right? So which means for SSB, the carrier frequency which I can use, right, for me to design, for me to be able to design a practical filter, right, to obtain SSB, the carrier frequency and this alpha are related like this. So it is 2 into 0.6. So it is 0.6 divided by FC should be greater than or equal to 0.01. It should be 0.01. I'm sorry, it should be 0.01, right? So which implies FC should be less than or equal to 0.6 divided by 0.01, right? This is 0.6K, right? This is 0.6K. So 0.6 into 0. So this FC should be less than or equal to 60 kilohertz, right? In one stage, this FC should be less than or equal to 60 kilohertz only. Why? Because I need to comply with this, right? I need to comply with this design constraint, right? So you don't have to this is explicitly not mentioned in your syllabus, but I think this is a very important point which has some practical considerations or applications, right? So depending upon this gap, right, this gap actually, what this gap between the upper sideband and lower sideband, it decides what is the maximum frequency content can be used. But there are certain situations wherein I'll have to use right, a carrier of 10 megahertz. I may have to use a carrier of 10 megahertz, right? So if I have to use a carrier of 10 megahertz, then what I should do is initially I should do a modulation here, right? Initially I should do a DSBSE modulation. Then again, this DSBSE modulated signal I have to consider as the new message signal. So that is what is shown in this particular question. So initially you are modulating, right? Then again you are modulating. So initially you are using f1 of 100 kilohertz. Then again you are modulating with an f2 of 10 megahertz. So why this is practically done is because of the design constraints. If you have to separate upper sideband and lower sideband, we should design a practical filter, and that practical filter's roll off and the carrier frequency has a roll off carrier frequency should be it's constrained by this roll off of practical filter or separation between USB and SSB. So this problem again, maybe what I'll do is I'll just solve it and post it in group. So just for instance, if you see something like this, you don't have to get confused. Why we are doing this is, right, this single sideband AM, which is practically used for, right, voice transmission, it has a limitation. So to overcome that, what we'll do is we'll use actually a cascade of modulators. Initially you will modulate, then again you will use another product modulator to translate the frequency. So this is also called actually frequency translation. You know what is frequency translation? If you multiply, right, any signal, right, if you multiply m of t with cos 2 pi fct, what will happen? Right, you will get, right, m of f minus fc and m of f plus fc, right? So the spectrum will be shifted right, or you can tell spectrum will be shifted right by an amount fc and also shifted left by an amount fc. So this is in a simple way is frequency translation. So the mathematical basis for this is, right, if you multiply two signals, cos A, cos B, right, so the resultant will have actually a content A plus B frequency content and A minus B frequency content. This is the mathematical basis, right, of frequency translation. So if someone is asking you what is frequency translation, so by multiplying it with a cosinusoid, right, you will get sum and difference frequencies. So if you want to retain only sum, you pass it through a band pass filter which allows only sum. If you want to retain only the difference, you use a bandpass filter which will allow only the difference, right? So that's it. So frequency translation is also a very important idea which we don't discuss here. Would actually what we'll miss out some of the very important practical aspects. So this is frequency translation. Frequency translation in detail, I bet you will be studying in 6th semester while you're studying the aspects of complex envelope and pre-envelope, all those aspects, right? But now, for instance, you know this much, right? So when you multiply with the cosinusoid, maybe you can relate it with what modulation property of Fourier transform or whatever, right? So yeah, so I think that's it. I've taken some extra time, say 5 to 6 minutes I've taken extra, right? So right, I'll stop presenting now. So if you have any doubt as such, please feel free to ask, right? So I thought maybe if I solve it and post it, you may have doubt. That's why this problem I've taken online, right? So remaining problems, right? So I'll solve it offline and post, right? If you have any doubt, please feel free to ask. Otherwise, you can leave. Right. Yeah. Thank you so much.